Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And within that playlist, I am creating little mini-series on the different types of experimental designs. And this one is part 4 in a little mini-series that I'm calling Repeated Measures, One-Way Fixed Effects, ANOVA. And here we're going to look at partitioning the sum of squares. And I really recommend that you watch parts 1 through 3 prior to this. But as a reminder, the model is y equals x beta plus air. And then this can be kind of partitioned into 3 parts, the mu, x tau, and x beta, where the beta and epsilon are normally distributed with constant variances. They're independent of one another. And here we want to partition the sum of squares to develop that ANOVA table and f-test. So if we look at the sum of squares total, which is defined as, the data points minus the grand mean squared summed over all possible values. Now within this, we're going to add a well-chosen 0. We're going to, now notice that this piece comes down here, and then that piece, is either one, this or this, but it doesn't matter. So this is 0, we add it and subtract it, add it, subtract it, add it, subtract it. So we've added 0 to this sum so it doesn't affect it. But what it allows us to do is when we take this, when we square it, so we take this times itself, this times that times that, etc. It boils down to this. Now in the next little step, we're going to show that all the interaction terms are 0. So what's left over, you get this squared, this times itself, this times itself, and all the, this times this summed is 0, this times this, all those little interaction terms are 0. Now, this term, there is no j index, right? So we're summing it n times, so the n comes out front. Here there's no I index, so it's summed a times. And this is what we just call the sum of squared error. And then this is the sum of squares treatment, sum of squares, the B, it stands for block, but it's the sub-between subject variability. Sometimes it can stand for between. And again, this is the error term. And so this sum of squares total can be uniquely divided into these 3 components. Now to show that the interaction term is 0, so this is an interaction term, from one of the cross products. And to show this is 0, notice in here that there's no j component in here. So if we can take that out of the sum, and then we're left with this piece, which is what this is. And so if you go this way, so here this is the y dot j bar. So that means we're dividing over the index I, so it's 1 over n, and then we take the bar off and it's just y dot j, which is a sum. This is a mean. But I do that way when we sum this piece here, we're summing over j, so it's just 1 over a and then y dot dot. And then here, there's no j, so we just get n of those. But notice that y dot dot bar is the sum of all the y's divided by n a. So the n cancels, and we're left with 1 over a y dot dot minus 1 over a y dot dot. So it's 0. And my mindset is, let's just show this is 0, and then this follows. And actually, the next 2 cases are the same. This is 0, and I'm going to kind of breeze over it because there's 3 pages of notes here. And then since this is 0, we look at this cross product and notice that there's no j in this piece here, so we can take it out, and then what's left over is this, and it is 0. And the third term is similar. Notice that there's we can switch this sum, and then there's no I in this index, so we take it out, and what's left over is this sum. And then you can easily, when you take that sum into each of those, you can show that it's 0. Now, maybe, perhaps a more intuitive partitioning is this. In the previous one, we just added a well-chosen 0 and boom, it divided into that. But this development I've seen in books, and it's a little more intuitive, not for some, not always, not all. So this is sum of squares total, which is this. And what we do is we add a well-chosen 0, which is y dot j bar. It's the mean of the jth subject. So then when you square that cross product term is 0, but then you're left with this. And this is the between subject variability, and this is the within subject variability. Now, this within subject variability can be split into the variability associated with treatment and random error, the sum squared error. And so this piece, which is this piece, is this. So then we add another well-chosen 0, which is yi dot bar, in here. We add it and subtract it, and then when we do that square, the cross product is 0, and we're left with these pieces here. And this is what we found on the first page to be sum of squares total, and this is sum of squared error. Now let's partition it in matrix form. Now notice that I took about a page explaining that in scalar form, but look how much it takes to do it in matrix form. So sum of squares total is this. It's this quadratic form, y transpose I minus j y. Now if we add 0 to this, add m and subtract m, then we take the y into each of those. And this is actually I minus m. This is always the error term, so that's finished. Now this piece, this contains the between subject and the treatment subject. Between subject and the treatment sum of squares. Okay, so if we rewrite what m is, now in this case we rewrite it, but we don't have to. But to make it look like the first page we do, and then here we write m. Now on a previous page we showed that m has the form m tau plus beta, m beta minus j. So this piece just comes down, and here we put a minus j with this and a minus j with that, and then when you multiply those y's in, we get this. So this is the error term, and remember, usually you just keep that as m, and it just really, to me, it simplifies things. But since we're in the repeated measures, one-way fixed effects ANOVA, you'll often see it like this. And then this is the sum of squares treatment, and this is the sum of squares between subject. And we're done. On page 3, we'll show that these equal the scalar forms. Now the degrees of freedom associated with each of these sums of squares is the rank of that matrix that's in quadratic form. So if we look at this, and look at the rank, this is a perpendicular projection matrix that we determined in a previous video in this little mini series. So it's the trace. And the trace of this is A, and the trace of that's 1, so it's A minus 1. And then the trace of, or the rank of this, and rank is the important part. And then since it's a perpendicular projection matrix, it's a trace, and we've shown that it's n minus 1. And then the rank of this matrix, and since it's a perpendicular projection matrix, I minus m, then it's the trace, it equals the trace, which is this, and so this is n times a, this is a, this is n, and this is 1. So this is the degrees of freedom associated with the rank. And it can be partitioned like this. Now, as a reminder, and I put a note over here, these are important to know the forms of each of these mean vectors. Now, And this we looked at in a previous part. So this is J times Y. So remember, this is a perpendicular projection matrix on the column space of 1. So when we pre-multiply something by J, it's going to shove it down onto that column space of 1, which is a constant vector. And we've shown that it is the grand mean times a 1 vector. M tau times Y. Remember, this is a perpendicular projection matrix, so it's going to shove it down onto something that has the same structure as X tau. And that's what we were calling the Y, the treatment mean vector. And then this is the between subject mean vector, or the subject mean, or sometimes called the block mean vector. And this is important when we try to show that the matrix forms are equal to the scalar forms. So sum of squared error is this. Now, if we can put this in matrix form, so the yi is, here's the y vector. The treatment means can be thought of as m tau y, right? This produces a treatment mean. This is a subject mean, or a block mean, and you get those with m beta y. This is a grand mean, and you get that with jy. Now, if you create two vectors and then vector product them, then you get this double sum back. But here, if we right factor out a y on both of those and then distribute the transpose, we end up with this. Well, it's actually this times itself, but it's idempotent, so you just get it back. And of course, this piece right here can be thought of as m. So this is a sum of squared error. So they do equal. And the same way with the sum of squares treatment. Now this n, since there's no j index, we can just sum it from 1 to n over j using j. And then this is the squared. So this is a treatment mean. So it's m tau y. This is a grand mean, so that's jy. Right factor out a y in each of those, distribute the transpose, we get this. So those are equal. The subject, between subject sum of squares, or the block sum of squares. There's no I in here, so we can sum it over I from 1 to a, and then these two equal. This is the block means, or the subject means, so that's m beta y, grand mean, right factor out of y, distribute the transpose, we get this. And so the scalar forms do equal the matrix forms. Now, to look at an ANOVA table, what we did was this. We separated the total sums of squares into between subject, treatment, and error. But if you think about what we did, the within subject we split into treatment and error. And so some tables have it like this, where you have the between subject and within subject, and then within subject you have treatment and error sum of squares. And there are some tables that just leave this row off, and then they just have the three, between subject, treatment, and the error, or the residual. And then the sum of squares, that's a number, and you get it from what we did up here. And then the degrees of freedom associated with each of those, which we calculated. Now the mean square treatment is just a sum of squares treatment divided by degrees of freedom. Same way with mean square error. And the f-test is the ratio of these two. And then that is under the null hypothesis as an f distribution, or follows an f distribution with numerator and denominator degrees of freedom, and we can calculate a p-value. Now notice that we didn't do the between subject test, and that's because it's of no interest to us. Now think about it. If you do a paired t-test, are you interested in the between subject variance? No, you're only interested in the treatment effect. And it's the same thing here. We're only interested in the treatment effect. Is it significant or not? We're just controlling some of that error by adding, repeated measures on a subject. Okay, so here's the final note, and we'll call our quits for today, is why use a repeated measures design instead of a completely randomized design? And so if we have A treatments, then completely randomized has different subjects in subjects, in different subjects in each treatment arm, where the repeated measures uses the same in subjects for each treatment. So the number one reason is that the repeated measures usually cost way less than a completely randomized design, right? You only need n subjects, and then you administer all 8 treatments to each n subjects. So it's less observations. Now let's assume the data came from a repeated measures design, but we analyzed it with a completely randomized design. So under completely randomized design, we separated the total sum of squares into treatment and error. And then a random repeated measures design, we separated into treatment. And this is the same, but the error we separate into between subject and error. Now notice that the error associated with completely randomized design is always going to be greater than or equal to the error associated with this. Now the degrees of freedom associated with this one is a little bit bigger than this, right? Because here's the degrees of freedom associated with each of those. But if the sum of squares between subjects is large, then the mean squared error in the repeated measure design is smaller than the mean squared error for the completely randomized design, making the repeated measures design much more powerful than the completely randomized design. And that's one approach and one reason why we want to use the repeated measures design. All right, well, that's all I have for this video. In the next video, we're going to look at the distributional properties of the sum of squares that we derived here. Well, I hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.